Welcome to chapter 11. This is a chapter on power and temperature. So power and temperature are first order concerns in the design of modern hardware and modern processors. That is basically because we have finite battery lives. In fact, as I was recording it, the battery of my wireless microphone ran out, and that's the reason I'm using a different microphone. That tells you how important power concerns are, because even the microphone has a small processor. So, to understand and appreciate all our power and temperature concerns, we will need some background other than out of order pipelines and caches. So, we will need a background of basic physics. That's not a lot of background, but still some amount of background is required. I would not say that it is absolutely backgroundless in that sense, right? So, some understanding, and this can be picked up. You can go back to your basic physics and fluid flow, heat flow, calculus fundamentals. Now the basic question is, do computers consume a lot of power? Well, you bet they do. They consume a lot of power. A few decades ago it was limited to few watts. Now it is the order of megawatts. So, if you consider large data centers, then they actually consume a lot of power, and it is so much that it can kind of bring a full city down. How hot do CPUs get? Well, first my gratitude to the person, to the unknown author who posted this image using a Creative Commons license. That's the reason I'm able to use it. So, basically what he has done is he has shown that in a regular processor it is possible to actually fry 2 eggs and create 2 wonderful poaches for an English breakfast with just the heat that the processor generates. So, it's like a stove, and in a typical desktop it would be order of 100 watts if there is GPU, more if it's a laptop, less, but we are talking of anything between 50 to 200 watts, which is sizable, it is substantial. So, a typical CFL bulb is around 8 to 10 watts, and we are talking of a lot of power here, right? So, it's enough for the bulbs and fans of a full house. So, that is what we are looking at, and that is just the power that a processor can consume, which is substantial. Hence, we care, right? Why do we care? We care because of the high energy bills. Energy bills are high. Also, if you consider data centers, the cooling costs are very high. So, you can think about it this way, that you spend a lot of money, let's say 100 units of money in buying your data center, machines for your data center, and then again you keep on spending a lot of money which would exceed 100 units of money easily over the long run for just cooling it. Insofar as mobile devices are concerned, you just heard about my experience where my microphone ran out, right? The battery in my microphone ran out, wireless one. Cooling costs are very high, and high power leads to high temperature. High temperature is a problem. So, we all know what a hot mobile phone screen feels like, how disconcerting it is when your fan starts rotating at a high speed in your desktops and servers. And higher is the temperature, lower is the reliability. In fact, the reliability decreases exponentially with an increase in the temperature. So, let's first look at a basic power consumption model, then we will look at a temperature model, and then we will see how do you manage power and temperature, how do you keep both within limits. So, power has primarily two components, a dynamic power. Dynamic power happens because of activity in your processor. Leakage power happens regardless of activity, it is dissipated regardless of activity, mainly because there are leaky interfaces via which ideally no current should flow, but it actually flows. Coming to dynamic power, well, we have all seen this. It's an inverter pair. So, you have your NMOS transistor over here, we have our PMOS transistor over here, again an NMOS PMOS pair. So, we have an inverter pair of I1 and I2. So, if the input maintains its value, then you will see that all the nodes in the circuit will also maintain their value. There is no flowing of current. However, if let's say the input changes, if the input is 0 and it changes to 1, then there will be a new flow of current, right? So basically what will happen is that unless current flows, then if let's say this was 0 to 1, then this will transition from 1 to 0. If it transitions from 1 to 0, then the current which is kind of at the gates over here, the charge which is at the gates, has to get discharged via these paths. And here again you would go from 0 to 1, which means that this point has to get charged primarily via this route. So there has to be a flow of current. Otherwise, your voltage, your charging discharging will not happen. And whenever there is a flow of current, it's going to pass through something, right? It's going to pass through some media. That media will have a degree of resistance that will cause a I square R heat loss, and this heat will directly get converted to heat. So we will convert, a degree of power loss. So we are essentially converting electric current into heat via this mechanism, where because of the flow of current, of course it's intermittent, I am not saying that it's happening all the time because these are PMOS transistors. So once there is a state change, there will be some current flow till the new state, and then there will be no flow after that and under ideal conditions. But for the state change, whatever current flows will lead to I square R power loss, which is a heat loss. And this is the dynamic power. So dynamic power happens when you have a switching activity in the circuit, which as you can see over here, switching is happening. The dynamic power dissipation will never happen if inputs maintain their values, switching is needed. The number of voltage transitions or switches determine the dynamic power. And of course, different parts of the circuit look different, right? You have small transistors, large transistors, transistors with a lot of fan out. Fan out means the output of one transistor is going as an input to many more. So all of these have a cost. So power simulation tools basically count all the transitions, and for every transition they have a power cost. So they know that how many milliwatts or nanowatts, it may be a better thing to say millijoules and nanojoules are spent for every transition, and that transition essentially determines what is the total power usage, which is the energy usage per unit time. So you typically find out in one cycle how much of energy you used, and you divide that by the cycle time. So the basic idea for doing all such simulations is to convert an electronic circuit into an RC network. RC network is a resistor capacitor network. So convert it to an equivalent circuit. For example, for an NMOS transistor, you would convert it to an equivalent circuit like this with two voltage sources, gate to source, source to body, a bunch of capacitors here. So the gate and source have a capacitance because there is a voltage across them. Similarly, gate and body, gate and drain, and so on. And you would replace them with these current sources, where the current is a function of the gate source and body source voltage. So this is this is traditional transistor 101, that any transistor is represented as an equivalent circuit in this fashion. And the advantage of doing this is that you can nicely compute the current flow and the consequent power dissipation. So let us now look at a basic circuit that has a capacitor. So it has a resistor and a capacitor, they are in series. We have a voltage source. So in the charging mode, the switch 1 is connected, switch 2 is disconnected, so the capacitor is charging. In the discharging mode, what we have is switch 1 is disconnected and switch 2 is connected. So then the current discharges like this. So let's look at the equation for charging. So in charging, this is the classic equation, can be derived quite easily, V by R multiplied with e to the power minus t by RC, where RC is known as the time constant. So this is the classical capacitor charging equation, where the voltage gets charged like that. So the total energy that is provided is CV square. The interesting thing is this independent of the value of the resistance R, right? That's very important to note. and that will be quite useful in our subsequent discussion. Out of this, half of it is stored in the capacitor, and sadly half of it is distributed as heat via the resistor over here. But the important point is the value of the resistance does not matter. So let's understand the capacitor charging discharging slightly better. So the idea is that even when I'm discharging, all the energy that is stored across the capacitor, half CV square, is dissipated as heat, mainly because a current flows, it flows through the resistor, and then there is an I square R loss. So of course, if I add the half CV square which is lost while charging and the half CV square which is lost while discharging, then clearly we are dissipating this much of energy. And if I just look at the current draw at the time of charging, that's actually CV square, where half of it is stored, half of it is discharged immediately. So we can say that the dynamic power is equal to CV square times the number of charge discharge cycles per second. If I take a maximum number, that will be proportional to the frequency, because this is the number of cycles that we have every second. But the point is that every cycle we may not have a charge discharge event. The reason being that our functional unit may not be active every cycle. If it is not active every cycle, let's say it's every active every alternate cycle. So what we will need to do is we will need to multiply this equation. So let's look at energy first. So I've removed the frequency term. Let's look at energy first. So this equation over here, E dynamic, energy dynamic, will get multiplied with a factor called the activity factor, which will be a number between 0 and 1. 0 would indicate no activity at all, and 1 would indicate full activity, which means that every cycle it is active, it's either charging or discharging. So keeping this in mind, let us move to the next slide. So this was reasonably straightforward. So what do we know up till now? So what we know is that any circuit comprising transistors can be broken down or converted to an equivalent circuit, which is an RC circuit with some voltage sources and some current sources. Broadly speaking, the energy that is spent in a charge discharge cycle is CV square. However, this holds for a single simple, RC kind of network. What about for a larger circuit? So in a larger circuit, we'll have many of these RC networks. So of course, I'm trying to simplify it. So we can then say that the energy dissipated, the factor of beta is still there. So of course, here the simplistic assumption that we are making is that throughout the circuit, the activity factor is the same, the transistor, the activity factor is the same. Furthermore, we are also assuming that, let's say if there are like n units and each one's individual capacitance is C1 to Cn. So furthermore, what's happening is that pretty much their energies are getting added. So you can think of this as kind of a lumped capacitance and replace it with C tot. So C tot is C total, or it's kind of the capacitance of the larger circuit. So as you can see, the formula remains the same, it's still beta times CV square, right? So the overall formula remains the same, subject to the assumptions that we have made. And again, when I compute the power at the level of the functional unit, that also remains broadly the same, which is beta times CV square multiplied with frequency, right, for obvious reasons. So that was discussed in the last slide. So what's the relationship between the voltage and the frequency, right? So it is clear that as the frequency increases, the cycle time, let's say t, the clock period, is 1 by frequency. So let's say if it gets doubled, this gets halved, which means that transistors have to charge and discharge sooner. So let's say if something was getting charged like that, then now, if you have a higher frequency, then it needs to get charged like this. So the point is that if I want a higher frequency, I have to have a higher supply voltage such that I can draw in more current and I can charge the capacitors sooner or faster. So there is a classical alpha power law which has been in use in different forms. Again, this is approximate, it's a rule of thumb, but this has been in use for quite some time, where the frequency is proportional to V minus the threshold voltage to the power alpha divided by V. So essentially the value of alpha kind of single-handedly determines the contour of this relationship. So in the older processes, which was late 90s, roughly 25 years from now, it was easy to kind of solve these transistor equations. So you could say that, look, alpha is roughly equal to 2. So then if you would ignore the threshold voltage, the frequency would roughly become proportional to the voltage. So if the frequency is roughly proportional to the voltage, since power is CV square F, right, proportional to that, you can say that power is proportional to the frequency cube, which basically means that if you double the frequency, then the power becomes 8 times. This is still used as a rule of thumb. It's not the case that it's not used. And but this is again, kind of indicative and suggestive. It's not a like a hard cut formula, right? So of course the value of alpha has changed quite a bit over the years, and also the difference between V and V threshold has also reduced substantially. It's not like 10 times more. It's only 2 or 3 times VTH, and alpha itself has come down. It is now a number that is between 1.1 and 1.3. So then this has completely skewed the relationship. So power is more like f to the power 6 or even more, and the reason is that it's everything is governed by this equation, and this is again a function of the process, right? So you have to see how the transistor is made and how it reacts to varying threshold voltage and varying frequency. So in this case, what has happened is that the power is proportional to some higher power of the frequency, which basically means that increasing the frequency is not an option that is available to us. If I increase it by 10%, my power will jump, like it will be 50% more. That is why I need to invest in more architectural tricks to enhance the IPC rather than increasing the frequency. That's why the frequency has remained roughly static for a while now. So now let's answer another question which is reasonably fundamental. So let us say that we have two designs A and B, and let's say as compared to design A, B is 10% faster but consumes 20% more energy for the same time. So which design is better? Or let's say it consumes 30% more power, which design is better? So this is very hard to, it's very hard to kind of argue it out, because clearly you're spending more energy, more power, and you are faster. How do I even compare? So that's why an ED square metric is used, which is kind of like a baseline, a gold standard for comparison. So let me write it down. It's a gold standard. I'll tell you in a second why. So let's, for the sake of simplicity, get away or get rid of a lot of rigor here. We'll make some simplistic assumptions. So ED square is essentially the dynamic power times delay Q. So energy is nothing but power into the duration of the program, right, that it executes. So let the duration be d for duration. So ED square is p cube, p into d cube, which is proportional. So basically P is proportional to V square F, right? The capacitance is anyway a constant multiplied with D cube. So now I assume that the voltage is proportional to frequency, which was the old model. Let's go with that. Then I further assume that the duration of the program is proportional to 1 by frequency, which again is approximate, right? I'm not saying it's exact if you consider accesses to main memory, but let's make that approximation that it is inversely proportional to the frequency. So if I double the frequency, the program executes in half the time. If I were to do that, then d cube would become 1 by f cube, and they would kind of cancel out, and this would become a constant. So this essentially says that, okay, subject to our simplistic assumptions, ED square is a fundamental property of the system and it's a constant, and essentially we should care about reducing the ED square rather than E and D separately. So this is how you can compare different designs. So it turns out that ED square for B is 0.97 times the ED square of A, and clearly in ED square lower the better, right? So the ED square is fundamentally used as a metric to compare different settings that have different voltages and frequencies. Primarily because you need to kind of reduce them to the same baseline, and ED square is a good baseline because it is independent of these quantities and it's a constant pretty much for a given system, subject again to our approximation. So let us now look at another kind of power dissipation. So this is traditionally also considered to be a part of the dynamic power component, but many people have been historically grouping this into a separate subcategory. So let's anyway see what it is. This is the circuit diagram of an inverter. You can clearly see the NMOS transistor over here. You can see the PMOS transistor over here. So there is a very brief period when both the transistors are conducting, when you are switching from 0 to 1 or 1 to 0. So during this brief period when both the transistors are conducting, there is a current that flows like this. This is known as the short circuit current. And essentially whenever there is a flow of current, it is flowing through these implicit resistances over here, and then there is a heat loss. So this heat loss is known as a short circuit power. This is quite different from the power that we have been considering. So regular dynamic power would either include a discharge path like this to the ground or would have a charge path like this, but you would not have a straight path. The straight path happens again for a very short period of time when essentially both the transistors are in their linear region and you are having some direct conduction. This is limited to 10% of the dynamic power, but many like to see it as a different category. So that's the reason it's called the short circuit current that leads to the short circuit power. So let's discuss another component of the overall power consumption known as the leakage power. It's also known as static power. So essentially in the transistor, right, if I consider any transistor, let's say these are the N wells and there's a p-type substrate, then you have your silicon dioxide and your gate here. You assume that the current is only flowing from drain to source. It is not flowing in any other direction. So the current is, for example, not passing between the gate and the body. It is not passing between the drain and the body, so on and so forth. So you are assuming that there are many ideal interfaces via which there is no current flow. But the fact is that there is nothing ideal in practice. It is a theoretical concept. Anything which is assumed to be ideal, there is still a very teeny amount of current that is flowing through it, and this small amount of current is known as leakage or the static current. So the leakage power / static power, if you integrate that across the billions of transistors in the circuit, then it's actually not that small. Then it turns out to be anywhere between 20 to 40% of the overall power dissipation, depending upon the technology, of course. But leakage then becomes substantial. So even if the transistor is in the off state, you are not switching, your dynamic power is 0, but you are leaking all the time. And the fact is that all the transistors that are connected to the supply are leaking all the time. Integrate this is a lot of power and not something that can be ignored. It is much more than the short circuit power. As I said, it is 20 to 40% of the overall. There are 6 well-known leakage mechanisms. Let us discuss one after the other. All of them kind of break the ideality of an interface. For instance, we have the PN junction reverse bias current, which basically flows from the N type to the P type, right, which is not something that you would normally expect. So this again flows because, so we will discuss what is the reason. So many times we have quantum mechanical reasons as well. So this current flows like this. You don't expect current flow like this, incidentally. Then we have sub-threshold leakage. That's a very important source of leakage, where even if the voltage is less than the threshold voltage, which means the transistor is in the cutoff stage, and ideally you expect zero current flow, you still have some current flow. So this is known as sub-threshold leakage, which is a significant issue. Then we have what is called gate oxide tunneling. So what happens is that there is this tiny silicon dioxide layer which is assumed to be a perfect insulator. So you assume that regardless of the voltage at the gate, there is no current flow like this, right? Nothing flows across it. But what happens that because of quantum mechanical reasons or because of the non-ideality of the interface, there are two different mechanisms known as gate oxide tunneling and hot carrier injection via which the current flows. Then let's look at I5. I5 is again when there is a current flow between the drain directly to the body. Because the body is often grounded or it can be connected to a separate voltage source. So we look at both. In any case, because of the voltage at the gate, there is a gate induced drain leakage, which means there is a current flow like this. This is also known as GIDL. Okay, so from its acronym. So again, this is there. And then the other is that because of the fact that the depletion regions kind of interact, we have the punch through current from the drain to the source. So we have the current going like this. So let's now look at each of these sources of leakage and talk about them. So let us look at the PN junction reverse bias currents. In general, in reverse biasing, you don't expect a lot of current flow. So that's the reason we have a tiny amount of current flow, which is leakage current. So the P side, which is the substrate in this case, is connected to a low voltage source, which could be ground. And the N side, which is the drain, needless to say, is connected to the supply, which is the high voltage source. So this is typically the case in an NMOS transistor, and this would be in a reverse biased situation because the N side is at a higher voltage and this is at a lower voltage. So what happens is that we have something called a band-to-band tunneling mechanism via which current passes like this. So before you ask me what is band-to-band tunneling, let me explain. So if you look at the energy levels of electrons, right, so then there is something very interesting that goes on. So this is basic device physics. This is interesting even for people who don't have the background. This still is an interesting concept because it kind of tells you that what exactly is the huge difference between a metal and a semiconductor, right, and an insulator. So essentially we have two bands. So we have the conduction band, which is a level, which are energy levels where you can carry current. So metals have a lot of electrons in that band, and essentially not all the places in this band are occupied. So this is also heavily quantized. So there are a fixed set of energy levels that you can occupy in the conduction band. So you are here, you can conduct, you can flow, you can conduct current. And if you are in the valence band, you kind of stay where you are and you don't conduct current. So what happens is that in the metals, of course, there is an overlap, which is why they are excellent conductors. But in the case of semiconductors, there are distinct energy levels and they are kind of non-overlapping, and in between them, their midpoint actually is known as the Fermi level. So for an electron to actually conduct current, it has to jump from the valence band to the conduction band. And here again, quantum mechanical principles apply of, there is a limit on how many electrons can be in which energy level and so on. But the key point is that the distance between them is not much. Because it is not much, with a slight potential or with a small push, in a doped semiconductor, electrons can jump across the Fermi level and the semiconductor can temporarily act as a conductor. So then the fact is that if I have a large electric field, then essentially you can pull electrons from the valence band of the p-type region. Where is the p-type region? It's over here. And you can kind of pull them up into the conduction band of the n-type region, which means that you can kind of extract the electrons. Electrons flowing this way means current flowing this way. So electrons can be kind of pulled up to occupy positions in the conduction band of the n-type region, and then they can conduct current, and then conducting current basically means a current flow, and the actual current flow is the reverse of the electron flow. So that's the reason you saw the direction that it you saw this direction over here, right, of the current flow in this direction, because the electron flow is in the reverse direction. And then we have an insulator. So an insulator, of course, whatever you do, regardless of the electric field or potential that you apply, the conduction and valence bands are separated. So the greatness of a doped semiconductor is that they are very close, and all that you have to do is you will have to apply a little bit of an incentive for electrons to jump to the conduction band, which anyway is done, but this is you can look at it in a desirable fashion or in an undesirable fashion. The desirable fashion is that this is why transistors work. In an undesirable fashion is it causes band to band tunneling, and because of this tunneling effect there is electron flow even across interfaces where you don't expect electron flow. This leads to leakage. Let's look at sub-threshold leakage. So this used to be very popular, it still is, and this one has a nice formula which is complicated, but at least there is a good looking formula which starts from here, ends here. Quite scary. So the idea is that the gate voltage needs to be lower than the threshold voltage for this kind of leakage to come in, which means the transistor needs to be in a cutoff state. In spite of being in a cutoff state, a tiny amount of current will flow from the drain to source, known as the sub-threshold, below the threshold leakage. We have a huge formula over here which I am not getting into. But if you kind of look at all of these things, so let me tell you, broadly speaking, we have terms of electron mobility, gate voltage, drain to source voltage. So VDS applies in a big way over here. So VDS comes here. And then the threshold voltage comes in, and the temperature, of course. So the leakage is a function of temperature. This is one thing that comes out. Previously it used to be an exponential function, but now it's not exponential, it's somewhere between linear and quadratic, mostly piecewise linear. So the leakage current is undoubtedly a function of the temperature. As you increase the temperature, the leakage current increases. This is the first takeaway point, which is a major point, that as you increase the temperature, the leakage current increases. This comes out from this equation. Needless to say, if you increase the supply voltage, the leakage current would also increase. Why? Because this increases, the negative decreases, then this increases, right, and then this decreases. Okay, let me say that again. This was confusing. Okay. VDS increases, minus VDS decreases, e raised to the power decreases, but minus of that increases, so the entire thing increases. Okay, I at least got it correct this time. So basically, if you increase the voltage, the leakage increases. So let's say I increase the voltage, leakage increases. I increase the temperature, leakage increases, right? And so the key point is, and in fact, if I reduce the threshold voltage, the leakage also increases. So as I said, anytime I try to miniaturize, anytime my temperature increases, the leakage current increases. See, here again there is an interesting leakage temperature feedback loop, because as the leakage increases, the power increases, which means the temperature increases, which means the leakage increases. So if this is a converging series, it's fine, but if the series is divergent, then it's a fatal case, right, for the processor. It's known as thermal runaway. So we will discuss this later in a subsequent slide, but broadly speaking, this is where we are. So more about subthreshold leakage, so we will just discuss what we discussed right now. That leakage current and temperature are related mainly via this term known as the thermal voltage, which is this here. Boltzmann's constant into T divided by Q, Q is over here. In any case, it's theoretically exponential, but as I said, in the typical operation range of 40 to 80 degrees C, it's between linear, piecewise linear most of the time. Some have approximated it as mildly quadratic, that's also fine. Then there are interesting things that happen in short channel devices. Incidentally, all our transistors which are small are essentially short channel. So what happens is that in a modern transistor, the source and drain are quite close to each other, right? Because the overall dimensions have shrunk, so if I consider this to be the source and the drain, they are quite close. So because of the effect of the drain to source voltage, the VTH, the threshold voltage changes. It was assumed to be a constant earlier. It's not a constant anymore. So as the VDS changes, the VTH changes. So you would expect the worst all the time. So that is Murphy's law. So it's just a philosophy of life that anything that can go wrong often does go wrong. And this is one example of that. So as VDS increases, that would increase the leakage anyway, but it would also reduce the threshold voltage, right? So how bad can life get? So VDS increases as it is fine, VDS increasing means that you have raised the supply voltage primarily because to sustain a higher frequency. So that would increase leakage, but that would also reduce the threshold voltage, but would also increase leakage. And it would increase the sub-threshold leakage current as well. Okay, that's kind of a double whammy for us, but in any case, the message is that don't increase the supply voltage, try out other architectural tricks. So this is known as a short channel effect. So then let's come to the third mechanism, which is gate oxide tunneling. So the main idea here is that if you consider the gate of a transistor, we have a silicon dioxide layer, then a polysilicon layer on top of it. Polysilicon is a conductor for all practical purposes, and then a metallic conductor to which the gate is connected. And then of course you have the substrate over here, and drain and source and so on. So the idea is that you are assuming that this interface is a perfect insulator, there is no current flow across it. That is sadly not true. The gate oxide as of today is quite thin, less than 2 nanometers. The electric field across it is thus quite high because the electric field is pretty much the potential difference divided by the distance. The distance is very small, the electric field is high. Because of the high electric field, what happens is, owing to quantum mechanical reasons, current can flow through this. This is known as a tunneling mechanism, which as I said is a quantum mechanical reason. There are two kinds of tunneling again, Fowler-Nordheim tunneling and direct tunneling. In this case, electrons move into the conduction band of this oxide layer. Let's call it the SiO2, silicon dioxide layer, also the oxide layer it's called. Because there's an external electric field, so essentially they move into the conduction band of this, which basically means that even though this is an insulator and the valence and conduction bands are far away, in spite of that, some electrons end up in the conduction band of the SiO2 layer and conduct current. The other is that again, because of purely quantum reasons, electrons directly kind of jump from the surface of the silicon to the gate via these 2 nanometers, and that has to do with the quantum nature of the electrons, the wave nature, right? And that their position is uncertain, and then basically if you follow the quantum mechanical equations, you can see that one solution for them is that they directly jump from here to here, and that results in a current flow. That is known as direct tunneling, where you don't have to go via the oxide layer, which the first FN tunneling actually is. Regardless of their mutual contributions, both of them add up and they lead to current flow across the gate oxide layer, which till now we thought is kind of impenetrable. Hot carrier injection, well, so let me again redraw that diagram. So this is the silicon, right? This is the silicon dioxide layer, the so-called insulator. This is the polysilicon layer of the gate. This does conduct current, and then the metallic contact. So basically, in the hot carrier injection mechanism, from the SiO2 interface, electrons simply escape. So there are a lot of these carriers, and these carriers have momentum, right? And the moment they have momentum, they kind of push through. So if the gate especially is positively charged, so what will happen is that electrons will there will be so much of an electric field, they will simply push through and go here. If they push through and go here, effectively current is in the reverse direction, so it is coming down. So this is how they would move from the substrate to the gate. So this is not quantum mechanical tunneling, it is just plain old kinetic energy. It's like a long jump, right? It's a long jump across a canyon. So essentially what you are doing, even if there is a canyon over here and you are running, you as a person, you are running very fast, right? So you run, right? I'm not a great drawer, so as you can see, but still this is meant to be a runner, okay? And so then you run, and you just jump. And this is plain old kinetic energy, no quantum mechanics here. And this running and jumping that you can do if you have a sufficiently strong velocity, which electrons have because of the the voltage, the gate voltage, and the very small, very thin oxide layer. So this canyon is actually very narrow. Let's come to Giddle. We have talked about Giddle earlier. So this again is the diagram of an NMOS transistor, where as you can see holes and electrons etc. are accumulating. So the condition is that if the gate to drain voltage is less than 0, which means let's say the gate voltage is 0.1 volts, okay, and the drain voltage is let's say 1 volt. So the gate to drain voltage over here is less than 0, which means the drain is positive. Then holes will migrate towards the gate oxide layer because essentially there is a net electric field which is going this way. So they will, so basically all the positively charged holes are going to move up, right? It's going to push them up, right? Push it away from the high voltage part. So then what will happen that they will accumulate over here, and the holes will pretty much then kind of migrate into, so there will be this accumulation, right, migration into the surface. So essentially what is happening is that because this is pushing holes out, there will effectively be a current flow, and this manifests itself, or this is mathematically modeled as a perturbation to the threshold voltage, as we have discussed earlier. But the basic idea is that because of the positive charge at the drain, it is pushing out holes, and basically whenever there is a migration of holes which are assumed to be positively charged, that is leading or resulting in a current flow. Finally, punch through current. Punch through current, as the name suggests, is kind of a forceful current, right? So the word punch, that's what it suggests. You consider the transistors to be short channels, right? So this, anyway, the gate, this should have been slightly wider, but still, cut some slack for me, please. So if you consider transistors as short channels, what will happen is that these regions will be much larger. So the drain substrate and the source substrate regions will be reverse biased. In a sense, what will happen is this is of course a positive voltage, but what could happen is that this also could be slightly positive because there could be other elements connected after it. So if both of them are reverse biased, then essentially the depletion region of the transistors would extend, and by extending they could kind of merge, they could become the same, right? So then there would kind of be a connection of a depletion region between the drain and the source, and if the gate is not controlling the substrate very well, this would lead to a new kind of a conduction path, because in a certain sense, once the depletion regions join, in a certain philosophical sense, it becomes the same device. So pretty much highly charged electrons can move this way from the source to drain, or you can say that there is a positive flow of current from here to here, mainly because these have kind of merged and become the same device. So what I mean by a poorly controlled gate is that the gate is not stopping this. Ideally, what should happen is that if the gate potential is very strong, it should kind of push out all holes this way and pull up all electrons this way to ensure that such kind of a flow doesn't happen. But typically, gate voltages are also reducing to sustain higher frequencies. So that is why you can have a straight punch through current from the drain to the source. So let's look at some ballpark figures. So the dynamic power is a major component, 50 to 70%. The short circuit power, as we have discussed, is much smaller. And most of the time dynamic and short circuit is kind of bracketed in the same bucket. If they are put in the same bucket, leakage power or static power on the other hand is actually not insignificant. It is somewhere between 20 to 30%, sometimes even more. But of course, with a lot of modern leakage control mechanisms, it has managed to remain there. That said and done, leakage slash static power cannot be ignored. This is substantial. So now that we have discussed the power consumption model, let us now discuss the temperature model. Given that the temperature model is reasonably long and this is the most physics heavy part actually. There is some in the reliability lecture, but this is quite physics heavy. So I would suggest that readers should first at least look at some of their physics and differential equations and linear algebra fundamentals before they get into that lecture. So that will be the next one. We'll end this lecture right here. So we will discuss the temperature model. After the two models are over, we'll get into power management, which is power reduction, all kinds of power reduction, static power reduction, dynamic power reduction. Automatically reducing power reduces temperature, but again there are specialized strategies that are explicitly tailored towards temperature. We will discuss that at the end and finally conclude. That's the plan. So this lecture ends over here. The next lecture we will start with the temperature model.